everyone. My name is Ajay. I am the product lead for Edge ML Solutions in a product team called Coral at Google. We focus on bringing machine learning accelerators to the edge for edge applications, very similar to what the GE use case was. So we'll talk about the journey, how we got here, and where I see the industry evolving and where the next opportunities could be. So AI adoption overall, or machine learning adoption, is continuing to grow at a rapid pace. So this slide here, we are using the paper submissions at Archive as a proxy for the interest in machine learning. And this is through 2009 to 2017. And if you see the interest in terms of, as captured in terms of the paper submissions, has really gone through the roof. So why, right? So we heard one use case from GE, actually a couple of use cases from GE, but there are similar use cases across different fields in manufacturing, travel, very vast areas of interest from healthcare, transportation, etc. I'm not going to go through all of these in detail, but there's a lot of use cases where we have machine learning being put to use, and that is what is driving this adoption across the industry. So what does that mean from a requirement perspective? Is the need for compute to run these models is growing up rapidly. So if you look at the chart on the right side, if you'll see that from 2013 to 2019, there are newer models that are being added every year by researchers, with the focus primarily being on better accuracy and better results. So these models actually also end up needing a lot more compute. To get that higher accuracy, you need a lot more computing power. So the need for compute has gone up about 12x in 18 months, right? Every 18 months, there's a 12x larger need for compute. And 12x, the 18 months there, I chose that metric is important because that's how long it takes for technology traditionally to go from one technology node to the next, going from 28 nanometer to 16 to 7. That's actually increasing now. We'll talk about that later. And that jump in technology gives you about a 2x improvement in performance at the same power. But the need for compute is growing at 12x, so something has to give, right? So what do you do? So what's happening is that newer models, though, are being added every 3.5 months. So technology is definitely not keeping pace with what is being required. So that brought a gap in the industry, which was addressed with a lot of infusion by VCs into the field of hardware for machine learning. So traditional CPUs got more powerful, GPUs got bigger and more powerful and more power hungry. There's a lot of innovation that it drove as well. So Google went from designing TPUs. We got V1 out about 5-6 years ago. Now we are at V3 of the cloud TPUs. We worked on the edge TPUs, which are used in the Coral products that I'll introduce later. At last count, there were about 65 startups that had more than $15 million of funding. And 15 million, that number is again significant because that's how much it takes to tape out a new chip in a new technology node, right? So which means that about 65 new hardware accelerators should be hitting the market anytime now, and they're starting to roll out. And these steps are great. They aim at addressing the need for more compute, but primarily the focus has been, from research point of view, to run these compute workloads in the cloud. And most of the hardware that is being built is for running these workloads in the cloud. But so we talked about Google. Google created the cloud TPUs. The V1 was launched in 2015 for inference only. Cloud TPU V2 launched in 2017 for inference and training, about 22.5 teraflops per TPU. Right now, the current generation that is deployed is Cloud TPU V3, launched in 2018, increased the performance to 52.5 teraflops per TPU, and these are deployed in pods, which essentially are supercomputers in terms of compute capability itself. But what about the edge, right? As we heard from GE, and we'll hear from other speakers, given the theme of this conference, there's a lot of need for running compute at the edge. And what I mean by edge, being at Google, is anything that is not cloud, right? So it's pretty broad. But why do you need machine learning to be run at these edge nodes, which are outside of the cloud? So a few reasons here. One is your privacy. Imagine from a use case perspective, a camera that is looking out into the room in a retail shop, right? It's capturing data 24/7, but if you transfer all of the data to the cloud, it's a loss in privacy. And there are regulatory compliance issues that are coming across regions of the world that would actually prevent you from being able to do that. So, but if you want to extract information from these cameras, you can run inference locally at the edge by retaining your privacy in the local environment and transmitting only what we call semantic data or useful data to the cloud for long-term storage, retrieval, and analysis. The other is latency. I've used a self-driving car example here, but it applies to multiple things where you need to take decisions quickly based on what your models are telling you. So that's the other reason. Bandwidth is a primary reason. Going back to the camera example, if you stream a 4K camera, it actually uses 24 megabytes of data per frame. To have any meaningful information from a video, you have 30 frames per second. So that's 700 megabytes of data in 1 second that you're transferring to cloud, if that's where your long-term storage is. So not only are you using up your bandwidth, which could be used for other applications, but you're now storing all of that in the cloud, and then you're creating a big haystack, and if you want to look for useful information from that haystack, you again have to run a lot of difficult computation to be able to extract information. What if I only transmitted useful information to the cloud? It becomes an easier problem. I save on bandwidth, I save on cost of storing all this information, and when I need to extract value out of that information, it becomes easier because it's a smaller data set now, right? The need to be offline. There are many use cases, for example, oil refineries or oil grids, which are offshore, which may not have connectivity. In third world countries for healthcare applications, etc., you may not have connectivity. So you need to be able to run offline. So once you load that model, your inference model, onto these devices, you need it to run without any connectivity to cloud even. So that's the other use case. And of course, cost. So the cost is the cost of streaming, the cost of the actual hardware itself, the cost in terms of the power budget. So for all these needs, there is a requirement to run inferencing at the edge in a possibly unconnected environment as well, right? So for those applications at the edge even, it is pretty compute intensive. So if you take an example of an image that is downsampled to 224 by 224 and you want to run inference on it, let's say using a MobileNet V2, to get about 60% accuracy, it needs, MobileNet V2 needs about 120 million ops, right? But 60% accuracy, as we know as practitioners, is not sufficient. To get up to 75% accuracy, now you need 1.2 billion operations per second. And even 75 is not okay, right? To get to 90% accuracy, you need another 10x increase in the amount of compute that you need from these edge devices. So it really gets heavy pretty soon, and we need to solve that, right? So how do we go about doing that? From Google perspective, the same team that worked on the cloud TPUs is a part of the team, and we have colleagues from representing the team here, worked on something called the Edge TPU. It is an inference accelerator designed to run at the edge. The current generation that is out there is a 4 teraops design, runs pretty power efficiently at 2 watts. And my standing joke here is that the penny that is shown there is just for reference of size, not cost. And but it is tiny, and it's got a low power envelope as well. It is optimized for vision applications today. It runs multiple state-of-the-art models at better than 30 frames per second, which is what you need to be real time. And we support TensorFlow Lite, which is Google's framework for running ML models efficiently at the edge. It's a purpose-built ASIC that was designed internally. And we are introducing that into the market and presenting to customers through the Coral platform. So Coral platform is something that enables customers to go from prototyping to scale and try out your ideas to go to production with the same tool chain of your hardware, your software, your ecosystem, and all of that. So the Coral platform it consists today is the way we are showing it is from prototyping to production. We have a development board that is available that uses the Edge TPU. The Edge TPU is connected to an industrial-grade SoC from NXP, and it brings out all the other I/Os that you might need in terms of USB, PCIe. It's got an Ethernet connectivity, HDMI, wired Ethernet as well, and as well as Wi-Fi. So that's a single board computer that is available off the market today that you can use and deploy your machine learning models in TensorFlow Lite. If you have an existing system that you're using today and you just want to accelerate that, you have an existing host, you can use the USB dongle. It's just a thumb drive form factor. You can plug it through USB 3 and you can accelerate your machine learning workloads there. Most customers are using that for prototyping. There are some who are using that for production if it fits their requirements perfectly. For production, what we have are two other components that are available already, the system on module and the PCI accelerator. The system on module essentially is the part that is under, let me see if I can get the laser to work here, that's under the heatsink here. This is just shown without the heatsink. So what we do is we provide the component which has all the active components that are there in the single board computer. We also provide the schematics for the baseboard, and you can design your own baseboard that accommodates the system on module, and you can bring out just the peripherals that you need. The PCI accelerator is a very small form factor. I have actually one lying in my bag. I should have shown it. It's a half a matchbook size. It plugs on to any existing PCIe, a mini PCIe, or M.2 slots that you might have. Mini PCI is typically used for Wi-Fi, and M.2 is used for SSD cards. And it'll show up as a PCI endpoint in your device, and you can accelerate your workloads there. So we're really trying to keep our pricing really low to enable machine learning workloads here. And maybe I should pause there and sort of very quickly explain why Google is doing this, right? We believe that Google has a lot of research that is being put into machine learning ecosystem in terms of TensorFlow, TensorFlow Lite, creating your model architectures. We have models that you can download and use. We believe extending that machine learning framework and tools include hardware availability would actually help a lot with growing the industry. And Coral is our effort to bring that to the edge devices. It also comes along with our own tool chain. So the development board has its own Mendel operating system that sits on it. It's a variant of Debian, and our own C++ and Python APIs for you to develop on, and a compiler that if you have a TF Lite model, you compile it so you get a binary that runs efficiently on the edge TPU. But now, with that being said, right, since I want to focus broadly, not just at what we are doing, if you look a little wider, what is happening in the industry is now there's a lot of hardware development effort that has gone into developing more powerful hardware to take care of these, to run these heavy machine learning models that have been created over the last few years, right? But the industry recognizes that the models have become a little too heavy and need a lot more compute. To address the computing need, we talked about what is being done by Google and by across the industry in terms of providing more hardware capability. But what the industry is also looking at is ways to optimize the network architecture itself to make them lighter, right? So you don't need that much hardware. So it's a rebalancing that is going on. So in terms of providing more compute, we talked about what we're doing. In terms of optimizing for newer network architectures is efforts such as quantization, which is making your model smaller so they can run on edge devices. We're doing embeddings. Pruning is where you lose very little accuracy by making the model smaller. Distillation and hardware-aware model development, etc. A sample of efforts at Google around that is, if you look at, and I'm not going to go into great detail, the slides actually, if it is when they are shared, will have links to each of these our blogs on Google. Quantization, this study that we did on quantization shows that for mobile net models, there's hardly any loss in accuracy when you quantize the models, but you end up needing much lower amount of compute to run these models. So that's something that we can look at. For joint training and distillation, the overall idea is that you have a teacher model, which is a bigger model that sits in, and it requires a lot more compute. But for regular inference, you don't need to run the teacher model all the time. You have student models that are a subset of the teacher model, which actually run for each of your instances, and the teacher model is updated based on what the student is doing as inference on a regular basis. We talked about pruning or not. So there was a study that we did on the effects of pruning and the loss in accuracy. As you see, ultimately, pruning can be, if done properly, can get you good enough results without losing accuracy significantly, right? And this was another very interesting area of study that we did. was around creating models by using machine learning itself. So we have a tool in Google called AutoML, which actually takes a base model and your data sets, and then using your data set, it optimizes the model for your data points. So we also provided another constraint to that AutoML tool, which is the hardware architecture for the HTPUs, and it created out a newer model by iteratively running it and compiling it, looking at the results, and it resulted in a lower latency and higher accuracy model as an output of that. So, which is something that we all strive to achieve, right? Better accuracy at lower computational needs. So, the summary is there's a lot of activity going on at Google and across the industry in terms of making your models more efficient. So that brings us to a thought point that what if the models become accurate enough or at a smaller enough size that you don't need all the hardware? So what if there's a rebalancing that we are looking at, right? So industry could get there. And if that happens, what should be the next focus on, right? So I think out of the 65 startups, there'll be a lot of companies that have hardware out now. And I think that given the reducing need for accuracy and the large number of hardware startups that will be there could be, again, a race to the bottom for the semiconductor industry, which I don't like because I come from that industry, but it could get commoditized again. But from a user perspective, that could be a good thing, right? Because you have a lot of options for cheaper, inexpensive compute solutions for edge applications. But the ecosystem today would look sort of like various AI models and frameworks that people are working on, and there'll be numerous now commoditized hardware architectures. But to get your models to work on one specific hardware architecture would require you to do a lot of fine-tuning around getting it to work, right? So what if there was a common intermediate representation that would take away all of that? So you can deploy whatever your framework or network architecture is on whatever distributed compute that is available to you in a heterogeneous process. So Google's effort at that is MLIR, that was recently open source to LLVM. I know Facebook teams working on something called Glow along similar lines. The idea is you bring whatever your models are on different frameworks, and MLIR is basically a tool suite that works on importing your graphs, different steps on optimizing and converting your graphs to generating code based on understanding of what your eventual target hardware is going to be. It could be TPUs or HTPUs or CPUs or FPGA. And since it was announced, there's a lot of partners that have signed on to the MLIR initiative, including, of course, the TPU team at Google, but also ARM and NVIDIA and AMD, Xilinx, etc. And 95% of essentially the world's hardware accelerators are on there. All Android phones are on that framework, so 4 billion mobile phones plan to use it as well. So that's what I think where the next innovation is likely to come from at Google and outside. So some other areas where AI is evolving is around model development, right? So when I talk to customers, they now see that we have hardware that will be available pretty quickly in a very robust way. And they have use cases that they know are going to benefit from availability of machine learning infrastructure, but they are not sure how to bridge that gap between converting their use case to actually running a model on a hardware so they can extract value. So I think that is a gap that I'm not seeing somebody address directly in terms of how do I write a model that can run on this hardware that you're saying is available now and extract value out of it. So right, I think that's a gap where the industry can jointly focus on, either by creating custom models or teaching people to train. So overall, the industry is moving, to summarize, from being a cloud-focused initial researchy project to actually having a lot of edge focus as well, especially for inference. The initial focus was just on hardware, on providing a lot of hardware infrastructure, but that has moved to adding on more powerful hardware with better optimized software and frameworks. We're moving from being specialized to generalized. So we want one hardware architecture, one software architecture and framework to be able to address multiple needs. So you don't need to be true custom. We've gone from being manual to automated, as in the result with the efficient net edge TPU. And I see that as one field where there'll be a lot of innovation in the future, where there'll be a lot of automation in terms of model development. And of course, we'll go from being more expensive to hardware getting commoditized, hopefully solutions getting much cheaper and more readily deployable. So I think there are a lot of potential areas for innovation and development in the AI machine learning space overall, in the edge and beyond. And as an industry, as a group, I'm looking forward to the next few years to understand what's coming. All right. Thanks a lot. I can be reached at my email if you have any questions or comments. I welcome those, and I can take some questions right now for the next 5 minutes. Any questions?
Yeah, what is the most advanced product you have in Google as far as this topic with cars, car technology?
So Google, of course, as you know, has Waymo. So that is an arm which is actively working on autonomous vehicles. There's Maps is another group which is providing maps for automotive applications. We have Android Auto for cell phone applications that you connect onto. So I think it's a very interesting space, but you have to be careful because autonomous vehicles are it's a life and death matter, right? So you have to be really sure about the robustness of your technology stack before you release it. And I've driven in one of the Waymo cars. It's really much better than anything else out there. My wife owns a Tesla, so I'm comparing those two unbiasedly, if you can believe that. It's really awesome in terms of what it can do with hands off. But I think they're taking their own time, making sure that the stack is really mature before they release anything out there.
Yeah. So what do you think something to startups to work on reducing the computational complexity of AI models, as you mentioned, when they are competing with open source platforms?
So I think there are two different aspects there, right? One is the platforms and one is the creation of the models itself, right? So the platforms are sort of enabling users or startups to make smaller, lighter models. So the way I see it, with all of what Google is doing and other big companies are doing, is sort of covering 80% of the stack in terms of providing the frameworks, providing the hardware that you can run your models on. What is missing is the remaining 20%, which is making it specific to a certain application, right? An automotive application versus what the GE use case is versus an application in a healthcare space or in a manufacturing location or a security application. That last 20% is specific models that you need to build for that particular use case by using their data sets, right? And that is the part where you need a lot of focused vertical effort, which is what is missing in the industry, and which is what I think the rest of the frameworks can allow you to do. Any other questions? All right.